Even if these pushes are quite small, resonance will result. This vibrating tuning fork sets the surrounding air molecules into harmonic motion. Because air works as an elastic medium, it's a good conductor of traveling oscillations or waves. Each oscillation gently and rhythmically pushes against the air, sending out waves at the natural frequency of the tuning fork. When the pitch of the note struck on the piano is the same as that of the tuning fork, even if the fork isn't actually struck, waves from the piano can disturb it and set it into motion by means of resonance. The tuning fork and the piano string are examples of naturally oscillating systems. And though they appear more complicated, they obey the same basic differential equation as the simple mass on a spring. Like a mass on a spring, they have an internal force, F, that naturally opposes any disturbance, X. That means a differential equation whose solution is a sine function representing oscillations at a natural frequency, omega naught, that depends on the characteristics of the system, which are in this case K, the stiffness of the spring, and M, the mass of the bobbing object. This is another oscillating system with a natural frequency. In fact, the child and the swing are a kind of pendulum. The frequency may be 1,000 times lower than the frequency of audible sound, but the principle's the same. A slightly larger mass, this one with longer legs, has learned to provide her own periodic push by shifting her body weight, kicking forward as far as possible, and tucking her legs under. Correctly applied at the same point on each cycle, that is, in phase, this young swinger displays her mastery of the phenomenon of resonance. But a true mastery of the phenomenon is best achieved by starting with an oscillating force that doesn't produce resonance.